Welcome to qnawire.
This is problem 30 of chapter 23. In this problem we have a doorway and sound is being transmitted through the doorway, so we can treat the doorway as a single slit. So we are going to use the single slit formula. The width of the doorway, sine theta sub m, is going to be equal to m lambda. And m can take out the following values: plus or minus 1, plus or minus 2, plus or minus 3, etc. Okay, so what are we given in this problem? We are given the width of the doorway, which is 1.2 meters. We are given the frequency of the sound, 440 hertz, and we're going to use the speed of sound as 340 meters per second. Here we are asked to find the angular deflection we're asked to find the first and second angular deflection for the diffraction minima for this single slit. So here we would solve this equation. We would divide by W first. M lambda over W. Now here I can take the inverse side of both sides. However, we're going to see that if this argument is greater than 1, there is no angle that would satisfy this equation, because sine of theta is bounded by -1 on one end and +1 on the other end. So if this argument here, m lambda over w, is greater than 1 or less than -1, there is no angle to satisfy this. So here we're asked to solve for the first and second angular deflections. So let's do the first one. So the first one is when m is equal to 1. So sine of theta 1 is going to be equal to 1 times lambda, which is 1.2 meters. No, 1 times lambda, so lambda is the wavelength, which we haven't calculated yet, so that's lambda, divided by the width. The width is 1.2 meters. So how do we calculate this lambda? Well, the velocity of sound is equal to lambda f. So lambda is velocity of sound divided by f, is equal to velocity of sound divided by f. So we'll go ahead and substitute that here. One times lambda is just lambda, so I could go ahead and just substitute v of sound over 1.2 meters times that frequency. Let's go ahead and substitute all the values in. So sine of theta 1 is going to be equal to 340 meters per second divided by 1.2 meters times the frequency, which is 440 hertz. Okay, so hertz cancels out with the inverse seconds, and the meters cancels out with meters, so here we're just going to have a number. Let's see what that comes out to. (340) divided by 1.2 divided by 440, we get approximately 0.6439. And I'm going to save that in the calculator's memory, and then I'm going to take the arc sine of both sides. So we can solve for theta 1 here, because 0.6439 is within the bounds of sine of theta. So theta 1 is going to be equal to arc sine of that quantity and that comes out to be 40 degrees. Okay, so here we had no issues because sine of theta 1 is within the bounds of sine. Let's see what happens when m is equal to 2 and we're calculating for that angular deflection of the second order. So step 2, m is now going to be equal to 2. So let's go ahead and apply the formula. Sine of theta 2 is going to be equal to, well here, notice it's going to be the same equation here. Lambda is going to be substituted by b of sound over f. There's just going to be a 2 here. So I'm just going to go ahead and type that. 2 b of sound over 1.2 meters times f. This is just twice whatever we got here. So let's go ahead and multiply that by 2, and yes, we get approximately 1.28. And notice that this is outside the bounds of the sine function, so theta 2 does not exist. What this means is that there is only one dark fringe on the other side of the doorway once the sound goes through it. For that second order angular deflection, there is no diffraction minima of the second order. It doesn't exist. And as we keep on going, m3, 4, 5, this is also going to be outside the bounds of the sine function. So this concludes this problem.